Okay, let's keep moving along here, and let's start to look at how photons propagate and what happens when they start to interact with materials. So, in vacuum or in air, because air is really close to vacuum, the speed of light is 3 times 10 to the 8th meters per second. Okay? And pretty much in vacuum and in air, the electronic and magnetic fields only interact with each other. So you just got pure electromagnetic field effects. They're not interacting with any material because there's not much material there. Now, if I go to a medium that is composed of a dense collection of atoms, like a piece of glass, or a bunch of molecules, like a piece of plastic, for example, then the electronic and magnetic fields, they induce a time-varying response in the charged particles that make up the material. So the material is made of atoms, right? And each atom has all these electrons orbiting around it, right? And then I bring in electric field. Well, if the electric field, for example, was in this direction as it came across this, then it could, in theory, then shift all the electrons. So if this is electric field and this would be positive and this would be negative, then it could shift all these orbits down in this direction for the atom. So it kind of drags them down. And if the electric field reverses, then it could shift them. Instead of being down, it could essentially then shift them. Let me finish drawing this, sorry. It would shift them up in this direction, okay? And so the whole point here is that the electron orbits can shift back and forth kind of like a rubber band. You just shift it in one direction, it's elastic, okay? So, most of the motion for these charged particles is highly elastic, meaning that if the electric field shifts them, it's going to give the energy back to the electric field as it rebounds, just like if you were kind of pulling on a rubber band, okay? Now, this takes time. So if the electric field comes into a material and it's shifting the electron clouds around and kind of moving the atoms around a little bit because they're all charged, then it's going to take a little bit of time for the electric field to transfer to the atoms and then the atoms to give that elastic transfer of energy back to the photon. And so the more the material is able to do this, it will slow the light down. And so when you go to a material that has more charged particles per unit volume, roughly, that can move in response to the electronic and magnetic field, the slower the light travels in that medium. So, the speed of light in a medium is slowed down by the refractive index. So, refractive index, this term here, is basically a measure of how much energy the material can absorb from the photon, give it back, of course, but absorb from it, and therefore, as it exchanges the energy back and forth, slow it down. A nice analogy I like to think of is imagine a sprinter sprinting on concrete. They would be at their full speed, right? Take that same sprinter and put them on a really loose trampoline. It would actually slow them down because with every step, the trampoline would go way down and they'd have to wait for the energy to come back. Now, is there any energy loss in that system? No. The sprinter would keep moving forward, but they would be moving more slowly on the trampoline than they would be on concrete trying to run forward. And so you can think of refractive index being more like a trampoline. It slows the light down. So how do you calculate refractive index? Well, it is the square root of the dielectric constant times the permeability of the material, which makes sense because this is the amount of polarizability or the magnetic response of the material to these fields. And so as these go up, the refractive index goes up. As refractive index goes up, the light slows down from the speed of light in vacuum. So, let's wait. Let's do a quick calculation here because I remember the first time I did this, it didn't make any sense to me. So if I look up the dielectric constant of water, it's 80 at 1 kilohertz. But the refractive index of water is 1.33 for visible light. That doesn't make any sense. Why is that? If I put 80 into here, and I know I'm not going to have a negative permeability or anything, it's going to be 1 or greater, then the square root of 80 is certainly not 1.33, right? Well, you have to be careful when you try to calculate refractive index. Remember that most dielectric constants and permeabilities are reported for frequencies of around 1 kilohertz. Because if you look them up in a table, they're for electronics. Okay? That would be a wavelength of 300 kilometers. Not visible light, which is hundreds of nanometers, right? So generally, as you go to optical frequencies like visible, the permeability goes to 1, and the dielectric constant decreases as well because the charged particles can't respond fast enough to the increasingly fast change in electric fields. So optical frequency is really high frequency oscillation, and these just can't slosh around enough because this is moving so fast they can't displace their full distance. And so their permeability and permittivity is effectively less. And if you sub those values in, then you'll get the right refractive index that you would expect for visible light, which has a much higher frequency than 1 kilohertz. So here you can see, here's some example materials. Teflon, dielectric constant at 1 kilohertz is only 2. You look at the refractive index at 500 terahertz, which is effectively visible light, it's about 1.3. Silicon dioxide, 1 kilohertz, but then you can see, obviously, square root of this would be 2, but you can see in visible, the dielectric constant must be smaller because of that as well. And then titanium dioxide, dielectric constant of an 80 roughly, but its refractive index at visible light is only 3. And so again, the dielectric constant at 1 kilohertz drops substantially at 500 terahertz, which gives you then the real refractive index. But this is not the whole story. So now we know that dielectric constant, permeability, and therefore refractive index all change with frequencies. But how might that affect us in visible light applications? Well, we'll explain that in a second when we look at a prism in terms of how white light split into its colors. But generally, what I want to point out is that refractive index generally goes down with increasing frequency or shorter wavelengths. So as you go to shorter wavelengths, the refractive index goes down. Okay? And again, with the visible spectrum, 550 nanometers is about 540 terahertz of frequency. Okay? So refractive index is going down as we go to shorter wavelengths, but eventually at some point you hit resonant frequencies for general materials, so it shoots up. So if you look at refractive index, so if this was, I'm plotting versus frequency and I'm going down, refractive index is going down, but then it shoots up because there's a resonance. Then it goes down, then it shoots up because there's a resonance, it goes down and keeps going down. Well, it turns out that the visible spectrum here, so we're decreasing in wavelength, and here we're getting down to hundreds of nanometers. Here's the visible spectrum here. When you go into the ultraviolet, you're hitting one of these resonances where, even though refractive index is going down, it starts to shoot up again. Okay? I'm sorry, in this case, my wavelength is decreasing, so my energy is going up, so my frequency is increasing. But that's the same thing. You're getting close to a resonance here. And so in the visible spectrum, here's your refractive index of glass versus wavelength. So as I go to shorter and shorter wavelengths, the refractive index of glass is changing. Now look, it's not changing a ton, but it changes enough that it can affect optics substantially. Look at this example. There are two photos here. This photo is taken with a very special lens system, and this photo is taken with a standard lens that does not correct for the change in refractive index versus wavelength. And if you look at the edges, you can see all these colors bleeding out on the edges. And so this is something called chromatic aberration due to dispersion. Dispersion is the term where refractive index changes with wavelengths. Whenever I say dispersion, that means a material's property such that its refractive index changes with wavelength, and you can see how dispersion can really mess up optics here, where certain colors are not getting through the optics the same way as others, and you can see the colors bleeding at the edges. Now, let's take a step back and look a little bit at ray optics and simplify things down a little bit, and then we'll come back and we'll start seeing refractive index come back in. And so there's a couple postulates of ray optics, which is the simplest form of all the different ways to interpret optics. The first postulate is that light travels in the form of rays. That's easy. And so if I look at light for any object here, I could draw rays. This is a shadow of the object, and I could predict that by rays. Here's a hole, I could predict it by rays. I could take an image here going through a pinhole and see it form on the other side, just tracing it out with rays. Okay? The second postulate is that an optical medium slows light by the speed of light in vacuum divided by refractive index, and that would give you the velocity in that material. Well, we just talked about that on the previous slide. The third postulate is that the optical path length between any point A and B is refractive index times the distance. And so optical path length is different than just path length. It basically says, okay, here's your path length, you've got to travel a distance d, but because refractive index slows the light down, the higher the refractive index, it increases the effective length the light has to travel. If you have to go 1 meter in a material with a really high refractive index, the light's going to act like it's going to take longer to get through there because it's being slowed down, as though it had a longer path length. Okay? And so the term optical path length takes in distance and refractive index. The fourth postulate, and this is very important, light will travel between a point A and B, always taking the path that requires the least time. Always taking the path that requires the least time. This is Fermat's principle. So let's look at the case here for light going from air to glass. And we're going to talk about Snell's law in a second, okay? But we know that when light goes, if you remember from physics, when light goes from one medium with a refractive index of air like 1 to a refractive index of 1.5, it doesn't go in a straight line. It actually refracts, changes the angle like we see here. Well, if you look at Fermat's principle, you could predict this as follows. You could say, okay, which is faster, this one or this one? It turns out that even though this, if you looked at the length of this dotted line, is longer than the straight path, this one here is faster because it basically increases the path length here in the low refractive index medium, air, refractive index of 1, where the light is faster, and therefore it's able to decrease the distance compared to here that it has to spend in the high refractive index material where the light gets slowed down. So what it says is basically, I can find a faster path if I spend a little bit more time in the fast medium I travel in versus the slow medium, and that will be faster than trying to go through this straight line, because if I do that, I end up more distance here in the slow medium than I would here. And so Fermat's principle actually predicts refraction. So let's talk about refraction in more detail. And so how you predict refraction is Snell's law. And so what's Snell's law? Well, here I have an incident ray of light here. And I could have a little bit reflective. We'll talk about that more later. Here's my optical axis, which is perpendicular to the surface. And my incidence angle is theta here. I can see that here too. Here's the air. Here's my medium here. Light comes in. Perpendicular surface, I've got my incidence angle theta. And so out here, the first part of this equation, I've got my refractive index out here, N1, 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 times the sine of my incidence angle theta 1. Now, Snell's law gives me the amount of bending I'll have as the light goes through this interface to theta 2. Inside here I've got N2, and then I've got theta 2, the refracted angle, again with respect to 90 with the surface normal. So it's with respect to the surface normal there. Okay? So we'll look at this in a little bit more detail, but this was predicted by Fermat's law. But let's use Fermat's principle and some simple trig to actually prove and derive this. It's really simple. So remember, the speed of light in each medium, let's say here and here, is the velocity is basically speed of light in a vacuum divided by refractive index. So speed of light out here, V1, is speed of light in vacuum divided by N1. We already know that. And speed of light here is V2 is speed of light in vacuum divided by N2. Easy, right? Now, let's look at the total time that it has to spend along each of these path lengths. So I've got L, I've got X, A, and B. And so remember, Fermat's principle set is going to say spend the least amount of time. So let's calculate for these parameters here how much time it would spend. Well, we know that time equals distance divided by velocity. Time equals distance divided by velocity. This distance here is just a triangle, right? So all I did was basically take this squared, square root of it, right? And that gives me the hypotenuse there. And I did the same thing here. Here's the distance I have to travel. This squared, this would be L minus X squared for this part of this, right? And I get the hypotenuse. divide that by velocity, I have the time it takes to travel here and the time here. So time here and time here. Now, Fermat's principle says get there quickly as possible. So I want to minimize my time to go from here to here. Well, I know that when I'm changing my variable x here, okay, if I go in the wrong direction, it'll take me longer time. If I go in the right direction, it'll start taking me less time. But eventually, basically, my point is that there are many different, I could go like this, I could go like this, I could do all these things, all these different paths, okay? But my point being that there is an optimal time at which you've got x, at which you've got x set perfectly where you're going to get to your minimum time traveled. Well, at that point, my change of time with respect to x will be set to 0, because basically this is an optimization experiment. If I'm looking at changing, here's my time versus x, basically there'll be some minimum here. And when I look at that, my slope will be 0 when I reach the minimum, okay? And so I'll say dt over dx equals 0. I'll basically take the derivative of this with respect to x, and there's my equation, and I'll set it equal to 0. Then I'll be able to equate these two terms because they're now set to equal to 0. I'll do a little bit of substitution here, nothing too fancy, and I end up with this here. And then what I want you to notice here is that I've got velocity here, velocity here. This stuff all right here, this is just sine of theta 1. And this stuff all here is just sine of theta 2. And so then I end up with sine of theta 1 over velocity 1 over here, sine of theta 2 over velocity 2 over here, velocity on this side. And I know that my velocity, right, is refractive index, is speed of light divided by refractive index. I'll substitute that in, so I have n1 over c, n2 over c. Well, c is equal, that's a constant, right? So I'll get rid of those terms, and lo and behold, I'm left with Snell's law here. So what I used is some simple trig and Fermat's principle, and now I've derived the the Snell's law for you from just using simple trig and a simple derivative and minimization experiment. So let's look at refraction in a little bit more detail. So here I am. This is called external refraction, where I'm going from a low index to a high index. And if you look at Snell's law, you'll see that when you go from low to high, it bends you more towards the surface normal. So theta 1 will be greater than theta 2. Theta 2 is smaller than theta 1, so it's bending towards the surface normal more. Okay? Then you have internal reflection, where it's the opposite, going from high index to low index, where you're bending more away from the surface normal as you go through the material. Now, eventually you'll reach a special case here. Notice as I'm increasing my incidence angle here, theta 1, it's getting larger and larger. At some point, I'm going to end up at a theta c, which is my critical angle, where I'm right here at 90 degrees. So my angle can't get any bigger than that, right? There's 90-degree angle there with respect to the normal. At this point, you get total internal reflection. You've reached the critical angle, because if you go beyond that, here's the critical angle, beyond that, the light is internally reflected. And this works great because there's no optical loss. It's not like a mirror where there's some loss. Basically, you get perfect reflection of the light with no loss, and it's trapped inside this medium. How do I calculate that? Well, it's simple. If you reach it at the point where my external angle here becomes 90, so I'll substitute 90 in for theta 2. That becomes 1. I'll move n1 over to this side. I'll have n2 over n1. I'll take the inverse sine of both sides and end it with theta c equals the inverse sine of n2 over n1. That allows me to determine what is my critical angle here at which I get total internal reflection. And so if I have a prism like this, the light gets reflected at this surface because you've got total internal reflection. If I have an optical fiber, the light is trapped in the fiber because I have total internal reflection, because the light is traveling within the critical angle. And this is why a prism splits the light out. What you do with a prism is you basically set the incidence angle for the light such that it's right at that critical angle. So I'm right at the point where I'm at close to 90 degrees, okay? Well, if you look at this sinusoid here, when you get close to 90 degrees, it becomes very, very sensitive, okay, to refractive index. And if refractive index of a material changes with light, you can see at that point this refraction becomes so sensitive with change in angle that it splits the light out, because blue light sees a higher refractive index than red light, and you get different angles because you're getting different equations for each of these, because N2 is different for each different wavelength of light. But you only get that when you get to this case where you're right at the critical angle and you get the strongest amplification effect of refractive index. So at that point, let's take another break and we'll work to wrap this one up.